For my final video tonight, I want to look at exponential and logarithm functions. Let's start with a nice f of x is e to the power x in red. And I'm going to ask Desmos once again, pretty please, calculate the derivative of this function for me. And in blue here, I get exactly e to the x. So the function e to the x is its own derivative. Let's think about what derivatives tell us. Over here, for negative values of x, the exponential function is small in magnitude, and that tells us that the exponential function is growing slowly because its derivative is small in magnitude. Over here, for positive values of x, I can see that the value of e to the x gets very large very quickly. And I know that's happening because the derivative of that function, the exponential function, is very large. So there's sort of a self-referential aspect to this exponential function. It's kind of funny that way. I think it's cool. Now, if I change this to a different function, so let's look at 3 to the power x, and that changes my curve here. Pretty please show me the derivative of f1. The curve in blue is still my derivative, and it's still an exponential function, but it's no longer exactly the same as the curve in red. So other exponential functions are not their own derivative. So what am I going to do here? Well, since this is just a recap, I'll tell you what the rule is. The derivative for an exponential besides e to the x, we have to take the natural logarithm of that base. And that is going to be multiplied onto 3 to the power x. So in blue and green, those are the same curve. So the derivative here is going to be natural log of 3 times 3 to the x. If I wanted this to be a 7, I'd have to have a natural log 7 to the x as my derivative. Does that agree with Desmos? Yes, it does. So in general, the formula for derivative of this kind of exponential is you take the log of the base, and then you just multiply that onto the front of the exponential. And of course, this still works for e to the power x. It's just that the natural log of e is equal to 1. So anytime we're talking about exponentials, it's natural to talk about logarithms too. Let's look at f equals the natural log of x. And let's calculate the derivative of this function. Let's have Desmos calculate the derivative of this function. D by dx. Function is f1, and we get this. What is this? So we have an asymptote here. That makes sense because this is a very steep slope, but it is positive. So we see very large positive values in the derivative. As we move out in the positive x direction, the logarithm function actually starts to flatten out. Its slope gets smaller and smaller, even though it is positive. And we see that represented in the derivative here. The derivative is telling us at each point what is the value of the slope here. So the formula for this function is, in fact, 1 divided by x. If I turn this on and off, you can see that's exactly the same curve, but you might notice down here that my derivative was only defined for positive values of x, and my formula, 1 divided by x, doesn't care about that. I can divide by negative numbers just fine. So what gives? Let me look at this logarithm function again. The logarithm is only defined when its input is positive. I cannot take the logarithm of a negative number. But if I did have a negative number, I could always throw absolute value bars around that and look at the function y equals the absolute value, y equals the natural log of the absolute value of x. I get this cool looking graph like this, still with this asymptote at x equals 0. Absolute value of 0 is still 0. Let me put that derivative back on there in black. Desmos says the derivative of this function looks like this curve, and now that is exactly the function y equals 1 divided by x. I see a lot of people who think of just log x and the derivative is 1 on x, but as a point of technicality, it is important to remember that there's an implicit absolute value bars sign. It's just that usually we work in the positive x domain and we don't have to worry about that so much. But we are totally allowed to work out here, and we get a larger domain for our derivative as a result. Okay, so this was my final video for recapping rules of differentiation. I would like to follow this up with some of the more advanced rules, like the product rule for derivatives, the quotient rule for derivatives, and so on. And I'll probably be doing that work not on Desmos. It's a bit more algebraic. So I'll be using a different way to present that. I hope you got something out of these videos, and as always, feel free to rewind and watch it again, and maybe that'll help too. Look forward to seeing you again. Bye.